Okay, in in test one material, we learned something about Newton's second law, that force is equal to ma. But if there are multiple forces, then you could say sum of the forces is equal to ma, or ma. And force is dealing with a linear in the linear world. But there is now the rotational world, and we shall now cover what is rotational force. Now, rotational force is something that we call torque. So if you've got a force, you know you're dealing with something linear. If you've got a torque, then you've got something that is rotational. And torque is typically used as the symbol lowercase tau. So a little, kind of like a little script T. Now, torque can be described as two different things. One is if you have like a fulcrum, a rotation point, a pivot point, and there is a force out a specific distance r, that this torque is the magnitude of torque is r cross F. So if you take F and multiply it by r, then you get the torque. Now technically, it's the part of the force that is perpendicular to this axis. So you could have a force coming down in many different directions. However, in Physics 213, we're not going to be dealing with that. We're just dealing with the pure 90-degree angle. And once I've introduced the other things, then I will go up to the door and show you all the different ways that torques work. Now, torque is also a vector. You can express it as a vector, and that is the r cross F. It's a cross product. Remember yesterday we covered the right-hand rule, and this is where the right-hand rule comes from. That the first vector is the vector from the rotation point out to the force, and then the second vector is the force out at that distance r, so r cross F. And notice yesterday's lesson, A cross B does not equal B cross A. You have to take the order of these vectors very seriously. It has to be r cross F. If you've got F cross R, then you will get the opposite vector of what's going on. The other way that torque is expressed is similar to this, is that the sum of the torques is equal to I alpha. Now, this is the rotational version of Newton's second law. Instead of the sum of the forces, you have sum of the torque. Instead of mass, you have rotational mass, moment of inertia. Instead of acceleration, you have angular acceleration. And so what this does is, if you've got a torque, this pin will start to rotate and rotate faster and faster and faster and faster and faster and faster and start spinning. So if you've got a torque, the terms that I use are spin up, as in rotates faster, and spin down, rotates slower. Yesterday, the examples that we were doing, omega was a constant. So because omega was a constant, the sum of the torques is equal to 0 because there was no angular acceleration. In some of the two favorite phrases that I have, in addition to no friction, yay, no friction, is translational equilibrium and rotational equilibrium. That those two phrases, if you see it doing nothing, I mean nothing, it is in translational equilibrium and in rotational equilibrium. And if it is in those types of equilibrium, you know for a fact, like we've said before, that the sum of the forces is equal to 0. Much like we had in terms of the derivation of what a normal force is. In rotational equilibrium, the sum of the torques is equal to 0. So in the translational equilibrium and rotational equilibrium, the linear and rotational accelerations are not observed. They're 0. And if you see those in terms of a problem, you should be very happy. Now, talking about what torque is, the Ole Miss way of opening up a door, it's the obvious. You pick the point furthest away from the hinges. I mean, it's just obvious. Now, this door has an automatic closer on it, so it puts a little bit of torque in the other direction. And so, when I apply a force, this is the R. The distance from the hinges to my hand is R. And so, right now, I can apply a little bit of force, and that allows the torque to be sufficient enough to overcome that and open the door. However, what happens when I push closer and closer to the hinge? You can do this as an experiment in lab or wherever you've got a door. And what happens is it gets a little harder. And the closer you get it toward the hinge, it gets really hard. And then you lose it. So this is where R is the greatest, and this is where Ole Miss students open their doors. This is the shortest distance. This is where state fans open their doors. And so that's why they could never get into school, because they just can't open any doors. So that's why they just hang out in fields. So it's this, some people call it the lever arm. It's the distance from this rotation point out to here. And what we're going to do after one more example is work through the right-hand rule and the understand torque, and we're going to talk about rotationally accelerating objects. And then we'll basically have covered all the material that we need for test 2. Now, as a reminder, problem set 4 is due at 6. If you want to turn it in first thing on Monday, that's fine. My mom and dad are here in town today, so I'm going to leave with them and we're going to go gamble and eat puppet chicken. So, when you have a bar such as this, and it's doing exactly what it's doing right now, what is it not doing? It is not rotating. It is not moving up or down. It's not moving left or right. It's not moving forwards or back. So you know that the sum of the forces vertically is 0. It has to be, otherwise the bar would go up anyway. The boring ones are the side to side and forward back. There are no forces acting in that direction, so you can ignore those. The other thing that you know is it's not rotating. The one thing that I need to get across to you is think of my hand as the rotation point. Is it rotating around here? Is it rotating around there? Well, ignore my right hand. Is it rotating around this point? So you can safely assume is that any point here along this stick, you could say that it's not rotating here, or you could say it's not rotating here. It doesn't necessarily have to be at the fulcrum or at a pivot point that looks obvious to pivot. And we're going to use this to solve torque bar equations. A torque bar equation typically looks like this. We'll start very simple. You have one mass over there, M1, one mass over here, M2. It's not going to be to scale. The distance from the pivot point out there is R1. The distance from the pivot point out there is R2. R2 is 2 meters. R1 is 1 meter. M1 is 4 kilograms. So there are two questions that I'm going to ask for this. One is, what is the value of M2 such that the system balances? And then what is the normal force of the fulcrum on the bar to keep the bar level or suspended at that particular point? In problems like this, in all the torque bar problems, and most likely you will get one on the test. So, right-hand rule, Atwood's machine with energy, torque bar, rotation, which typically means that, well, if I can just illustrate it right now, right-hand rule, rotation, that's the appetizer, that's 1, 2, Atwood's with energy. And 3, torque bar. That's what we got. And so one of the things that typically is not covered in test 2, except for the multiple choice, inelastic collisions. I haven't been really able to get a good inelastic collision problem into test 2, but it does show up on the final. Yes.
This might be a stupid question, but is rotation the same as elastic?
No, no. There's elastic refers to a collision. Rotation refers to a motion.
Okay, so we don't have an elastic problem.
Oh yeah, and I sent out an email yesterday. I think it was problem 4 on the problem set that's due today. That was an elastic collision problem. Omit that. Don't do that one. Elastic collisions will only be covered in the multiple choice, never in a problem set or on a test, because it just takes too long.
Same for inelastic as well?
Oh, inelastic as a problem could be on the test, yes. I find it difficult to squeeze it into this. I don't know exactly I don't know how I would do that yet.
Have we covered rotation?
We're covering rotation now. We covered rotation yesterday too. The rotation yesterday was all about alpha equaling 0. These torque bars, alpha is 0, but a torque bar is its own type of problem.
Okay.
In the second half of this lecture, we're going to cover where alpha isn't 0. So we're still in an alpha equals 0 mode. You're welcome. And the question that you asked is probably being asked by half the class, so it is useful to answer that. When you see a problem like this, and I don't give you any restrictions on how to solve it, this is the easiest way to solve it. For part 1, you know for a fact that the sum of the torques is equal to 0. That thing isn't rotating. And for number 2, you know that the sum in the forces in the vertical is equal to 0 as well. And so that's the way that you do it. Now, to do this, you're going to have to pick a point, pick a logical point for rotation. And typically for a problem like this, you pick the fulcrum as the rotation point, and you use A. Well, I say A. So the sum of the torques about A is equal to 0. Well, what are the sum of the torques? The sum of the torques is the sum of the products of the radii with the forces. So R1 F1 and R2 F2. Now the way that it's set up, torque 1 is the A, the distance from the rotation point to the mass, or R1, times the force associated with M1 or M1G. R2, the distance from the rotation point to M2, multiplied by its gravitational force, or M2G. So this becomes R1 M1G R2 M2G. This is where the right-hand rule comes into play, because you notice I have not put signs in front of the parts in this equation. What you do is you go first vector, the R, second vector, the direction of the force, and then the third vector is the thumb. If it's thumb out, it's a circle dot, and thumb out is positive. Thumb into page is that, and so we get negative. So thumb out positive, thumb in negative. So the first vector is to the left of the fulcrum. Put my fingers to the left. That force is towards the bottom of the page. Thumb points out of the page, so it is positive. This force here is to the right and down. So to the right, down, thumb goes into the page or negative. And that is how it works. That determines the sign. From the side, it looks like this. If you were looking at it from the top, fulcrum's there. Both of these forces are into the page, because into the page in this particular rotation is down. So R cross F, torque 1 looks like this. R cross F, torque 2 looks like that. And so now you could see how the torques oppose each other. So the torque vector is this vector that just sticks out from the object. And so this is how people can associate rotation with how they add up and cancel. So this becomes R2 M2G equals R1 M1G. The G's cancel. I'm looking for M2. M2 equals R1 M1 over R2. So R1 is 1, M1 is 4, R2 is 2, so it's 2 kilograms. And that's the mass of 2. You start with rotational equilibrium, you assign a fulcrum, you identify your torques, and then you look for what's missing. The second part is F sub y, sum of the forces vertically. The up forces and the down forces have to cancel. In this particular case, it's easy. Anything up is a positive sign, anything down is a negative sign. So positive F minus M1G minus M2G. So M1G plus M2G is equal to force. That is 4 times 10 plus 2 times 10. So that is equal to 60 newtons. And that's the force. That's a very simple torque bar equation problem. And let's study it a little bit more, because typically someone asks this, and so I want to address it. When I'm summing the torques, I'm summing up the forces which could cause rotation about this point, right here. I chose A to be at the fulcrum. So why did I not put, we've got M1G and M2G, why was there no F in that particular equation? Why did I not consider the normal force from the fulcrum onto the bar at that pivot point? Dun, dun, dun. What's the distance from the force to the pivot point? 0. And so what's 0 times anything? 0. So the advantage of picking a rotation point at a force, you can effectively eliminate that force and don't have to think about it. It's much like my hand at the hinges of the door. I could push infinitely hard, but it's still not going to cause the door to open. Granted, it may rip the door off the hinges, but it would not cause a rotation. The fun thing about these torque bar problems is you don't have to pick the obvious fulcrum. You could pick any point. You could pick here, here, there. It has to be a logical point. So in this particular problem, I have two unknowns, M2 and F. I picked A as the rotation point because I could effectively eliminate F and solve for M2. What I'm going to do now is the same problem, but I'm going to pick B as the pivot point and solve for F. So with this, I know for a fact that the sum of the torques around point B are equal to 0. Now there are two torques that could cause a rotation around that point. This one, its distance is 0, so I can ignore it. F is a distance R2 from that pivot point, and M1 is a distance R1 plus M2, or R2, to the pivot point. So my two torques are F, R2, and M1G, R1 plus R2. R1 plus R2 because that's the distance from there to there, from the pivot point to the force. F is distance R2. Let's plug in our signs. In both cases, the forces are to the left of the fulcrum. For that one, the force is down, thumb points out of the page, or positive. The force over here is to the left, but it is up the page, so the thumb goes in, or negative. And what I'm going to do, I'll do it again, but I'll do it up at the drawing. So there's the pivot point. That's a force to the left. Force is down the page. Thumb points out, positive. This force is to the left of the rotation point, but it's up. Thumb goes into the page, or negative. And so that's what the right-hand rule is for. It's a calculator to determine signs. Now some people say, oh, rotate counterclockwise, rotate clockwise, whatever. The way that I do it is with the right hand rule. Because the right hand, as long as you're using the right hand and apply it correctly, it will give you the right answer. So our only unknown in this case is F. So M1G, R1 plus R2 is equal to F R2. So M1G, R1 plus R2 over R2 is equal to F. So M1 is 4, 10, R1, 1, R2, 2, R2, 2, and that is equal to F. 40 times 3 is 120. 120 divided by 2 is 60. And so they match. You can solve M2 now by just doing the sum of the forces in the vertical. Minus M1G minus M2G plus F is equal to 0. So F minus M1G equals M2G. So F minus M1G over G is equal to M2. Force is 60 minus M1, 4 times 10 divided by 10. That should be a 60. 60 minus 40 is 20 divided by 10 is 2. So they match. So you can pick any pivot point that you want. You just have to pick a point that makes sense. Now, the last example that I'm going to do for torque bar problems is one that make it a little bit more complex, but the procedure is still the same. Is what's really funny about this particular problem is actually I was giving the review session in this room for 213, and it was a 2-hour review session, and halfway through the review session it was really weird. I guess there was an organic chemistry, something was going on, and like half the class got up and left. And now granted, it's a review session, they can do what they want. I don't punish them, but I do award those who stay. And one of them asked, like, could you give us a torque bar problem that could be on the test? And that question was asked immediately after 40 people walked out of the room. And I said, you know what? This could be on the test. And what I did is I put this on the test. M2 is 40 kilograms. That distance is R2, which is 2 meters. This one is M1, which is 5 kilograms, and its distance R1 is 0.75. Make it a little more interesting. This distance over here, R3, is equal to 2.5 meters. So the two questions are, this is like a ceiling with a string holding up this end of the bar, and I want to know what that tension is, and I want to know what the normal force is from the fulcrum onto the bar. It's a simple torque bar problem. You use the same principle. It doesn't matter what, I mean, these torque bar problems can get all sorts of weird and complex. But you just follow the two things. One, pick a pivot point that's sensible. The two sensible points are here and there. It doesn't matter which one. I'm going to choose this one. Why? I don't know. I flipped a coin. And so that is the pivot point A. Sum of the torques around A is equal to 0. How do I know that? This thing doesn't rotate clockwise, counterclockwise, or whatever. There are 3 torques that interest me. F is at the rotation point, so I can forget about F because F times 0 is the torque of F at A, and if R is 0, that torque is 0, so I can ignore it. So my 3 torques are M1G R1, M2G R2, and then T R2 plus R3, like that. So those are the 3 torques. Now let's figure out the signs, and what I'm going to do is probably the best way is to just go up to the board and do this. The first torque is caused by a force, M1G, which is to the left of the rotation point. So left, down, out, positive. Second force, M2G. M2G is to the right of the pivot point. Its force is down, thumb goes into the board, or positive. Tension is a little bit different. It's not always forces on the left cause counterclockwise and forces on the right cause counterclockwise or clockwise. This tension is to the right. The tension now is up. Thumb points out. So that's positive. So the signs in this case are positive, negative, positive. And you get the signs from that. I have to solve for T. And you get this. So 10, 42 minus M15, 0.75 over 2.5. And one of the things that I'll definitely have is the math all set up before it gets to you guys, because there was one time on a test I gave bad numbers and it was just like, oh crud, this sucks. So I check and then I check again. The, oops. 169.4 repeating. newtons. So you could just say 169.4. And that is the same thing that you always do on a torque bar problem. You sum the torques about one of the axis or rotation points, and then that's it. The second part, sum of the forces in y are equal to 0. Up forces are same as the down forces, F plus T minus M1G minus M2G. I'm looking for force, so M1G plus M2G minus tension is equal to 0. This gives me 5 times 10 plus 40 times 10 minus 169.4, and that will give you 280.6. And so that's the tension and the force. Oop, that's not a 0, that's F. And so that's a torque bar problem. A lot of people get mystified by it. But remember, it's the technique. Knowing this and applying that. Knowing that and applying that. And there you go. So that's a torque bar problem. Let me see if there's anything else. All right, what I'm going to do before we get into rotation with acceleration is we're going to do the right-hand rule, since it's all written down and everybody has a copy. So for those of you keeping score at home, this is what we're about to do, this game right here. Now, what's important about this is that when we're in a testing environment, the right-hand rule thing is not going to be up on the wall. It's going to be on your desk right in front of you. So what I need you to do right now is we're going to do the right-hand rule just by looking at the paper. Because a lot of people get confused with up on this paper is not always up in the room. Right now, the way that I hold it, C is towards the ceiling. Now C is towards the library. Now C is towards Kenan. Now C is towards the floor. What you have to do is you have to look at this page, ignore everybody else and how they're holding their page, and only think about what it means to you. The answer that you get when you hold it like this is going to be the same answer if you hold it like that. The one thing that I want to warn you about is don't move the paper, don't change its orientation during the test or during each problem. So I'm gonna sit, put it down like you guys would look at it. A cross D is what? So A is out of the page or towards the ceiling. D is that way. So what vector is aligned with the thumb, which is pointing towards the back of the room? The F. So A cross D is F. So with your paper, A is out of the board or towards the ceiling. D is that direction. Thumb points this way. What is the vector pointing in that direction? F. So that's it.
But technically, I would think of F as like going down, no?
Why do you think F is going down?
Because this is how it looks, like it's going down.
It's heading. Don't think, and this is what I've taught a lot of students, and so your problem is the same as a lot of others. Don't associate the vectors with specific directions. Because right now, F is towards, don't think of it as down the page, think of it as towards the back of the room. Now F is towards that wall. Now F is towards that way. So now let's do A cross D again with this being upside down. A up towards the ceiling. D is now that way. Now remember, you're not double jointed. Can I bend my fingers backwards? No, but I can curl it that way. Remember that the second vector, first vector, second vector. It's that curl. The fingers can't curl backwards. So if you're trying to flip your hand over, you're doing it incorrectly. So A, out of the board. Your D is towards that way. So thumb points that way, and again we get F. Second, C cross E. C cross E, whatever number 2 is. It's B. So in a normal orientation, C is towards the front of the room. E is towards the library. You did the same wrong thing that she did. When you curl your fingers, you don't see how your fingers can't naturally bend that way, but they can naturally bend that way. So C, I can't bend my fingers that way towards B, so what I do is I rotate my whole arm, and now I can bend it in the right direction.
So why isn't it F?
Because F in this particular orientation is towards the back of the room. It's down into the page. Think about it associated only with respect to the page. So right now, F is towards the back of the room. Now it's towards the floor. Now it's towards the library. Now it's towards Ken. You have to respect the orientation. Why would I not use A?
No, when would you use A?
When it's out of the page.
Oh, so we were pointing up?
Well, yeah. In this case, if you ended up with a thumb that's pointed out, that's A. Yes.
So if you're given a top A and B, if you're given something that crosses either A or B, then your answer will be one of those two.
Correct.
But if you're not given one of those two, then your answer will be.
It could be. Yeah. There are a lot of people who've been. They've been doing a lot of analysis on what, like. Yeah. If I go E cross F, I got a horizontal with a vertical, which means my only two choices are in or out, because you can't get left, right, in and out, and another left, right as the answer. All three axes must be used at the same time. F cross B. It's E. So F towards the back, B is into the page or into the ground, which means E.
So F is back?
The way that you're, let me see. F is back.
Yeah. And then C is down.
It's into the page. B is going to be that way.
Okay.
I'll probably, yeah. But the selection of which letter goes in which direction is going to be. Now I did have an individual during a test. They requested, they only learned it by holding the page up like this, and then they did this way, and they said, can I stand up during the test and do the right hand rule standing up? And I said, yes, on one condition. I get to take pictures. So I've got pictures of the dude doing the right hand rule standing up in the middle of the test. It's awesome. Once it clicks, then you go, oh, this is obvious. First vector, always curl naturally with your fingers in the second direction. If I have to do this, then I know I'm going the wrong direction, so I have to flip over and then do it. And that tends to be the biggest problem. And then misorientation of direction.
Question.
Yes.
When you start out with A or B or in or out of the page, how do you know what does your hand do?
If A is at the first vector, I go this. If I go into the page on the first vector, I go that. So whatever in or out, or this is out, that's in. The way that the page is like this. I had another person during a test, they were like two-seated, and so what the person in your seat did was they took their entire right arm and fully extended it across the desk of the dude next to it. And the dude just kind of looks over and goes, I'm sitting here, not doing it. Last one, D cross A. It's C. Did you get that? Good. D cross A is C. B cross E is F. So be able to do this now that you know the answers. Do this at home, work through it, and make sure that you understand.
A would be up.
Little d, B cross E, D, F. Very good. All right. For the last part of this test 2 material, so just I'm looking over problem set 6. We covered this yesterday. This is conservation of angular momentum. Then I gave you 4 torque bars to have fun with. One thing that will happen this afternoon, on any day that homework is due, we have tutors in the tutoring room from 1 to 6. So feel free to have fun talking with them. But on the front page of 6, there are these 3 problems. Those are the standard rotational problems if alpha isn't 0. You see a circle, you see an arrow with a force next to it. That is basically saying you have, like how I equate these problems to be, you've got a disc, you've got a rocket on the disc, the rocket is fired and it's producing a force that causes the wheel to spin up, spin up, spin up, spin up, spin up until you do whatever you got to do. So let's talk about this type of problem. When you've got this type of rotation, it's no longer sum of the torques is equaling to 0. It's now sum of the torques is equal to I alpha. In this particular case, alpha is equaling to 0. In this particular case, alpha is not equaling to 0. Now this opens up a whole new realm of what we could ask. There are equations that can be used in either case, and that is we have our linear equations of x equals x naught plus v naught t plus 1/2 a t squared, and we have v naught or v equals v naught plus a t. Those are the linear equations of motion. Now that we've got alpha being non-zero, it gets a little bit more interesting for the rotational equations of motion. So for the rotational equations of motion, it's theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And omega is omega naught plus alpha t. So these two equations are critical for understanding what goes on. The final angle is the initial angle plus omega naught t plus 1/2 alpha t squared. Omega is equal to omega naught plus alpha t. The thing that happens in most of these problems, if not all, is that in 99.9% of all cases, omega naught and theta naught are both zero. That the initial rotation is zero, and that the initial position of the angle is also zero. There is one example done in class where I talk about theta naught being zero, or being non-zero, excuse me. But that is only for one specific problem during a lecture. For your problem sets, for your test, for your final, theta naught will always be zero. You just treat it, you treat the initial position of the disk as as the origin. You just say that alignment is origin. Typically they start from rest, so you say omega naught is zero as well, and you're left with theta equals 1/2 alpha t squared and omega equals alpha t. And so things simplify considerably. There's some other equations that you need. As I've said before, vector addition, 2D motion, 1D motion, torque bar problem, there is a very set procedure that you follow in order to get the answers. With these types of rotation problems, just like the alpha equals 0 rotation problem, the solution gets a little bit more freestyle. There are many other equations that you need, and you'll need them at varying times. One of which is theta is 2 pi n, that the number of rotations is equal to, times multiplied by 2 pi, is the angle traversed by the object. So if you rotate 1 time, that's 2 pi rotations. If you rotate 3 times, that's 6 pi rotations, and so on. You know that 2 pi f is equal to omega. So there will be certain situations where you have to substitute in for that. There is radial acceleration equals v squared over r. There is v equals omega r. There is, let's see, what else can I throw in there? Since we're dealing with torques, torque is equal to Fr. Now notice I did Fr, not Rf. When you're dealing with magnitudes, I don't really care about the order. 3 times 2 is the same as 2 times 3. But A cross B, which is what we're not doing, is very much different from B cross A. So with these types of rotational, let's have a simple disk. The mass of the disk is 80 kilograms. The force of the rocket on the disk, we're going to say, is 40 newtons. The radius of the disk is 2 meters, and I'm going to be bad. I'm going to interchange little r and big R so often, but I'll keep it with little r. I want to know in 30 seconds how many times did it rotate? What is the angular acceleration of the object? What is my final omega? Let's see, what else? Oh, we'll keep it simple like that. What's my final omega? And then, oh, there was something else that I wanted. That'll be good enough. So in a situation like this, this is the one thing I needed to say. It starts from rest. So with a problem like this, how I typically do this is I just dump out equations onto the page and then just start seeing how they merge together. I know I've got a rotation, so theta equals 1/2 alpha t squared. And I know that that theta is 2 pi n. That introduces the idea of how many times did it rotate. I know time, I know I'm looking for n. So n is equal to 1/2 alpha t squared over 2 pi, or alpha t squared over 4 pi. So I get that. But I don't know what my alpha is. However, I know that it is a force is acting on the object causing an angular acceleration. So the sum of the torques, there's only one force, so one torque, force times R. That force times R is equal to I alpha. So alpha is FR over I. Now before I plug in alpha into this, alpha has an unknown. I do know F, I do know R, but I don't know moment of inertia. I was not given that value. However, I know that it is a disk. So this becomes FR over 1/2 mass of the disk, R squared. That's the moment of inertia of a disk rotating about its center point. One of the R's cancels, and my alpha is 2F over mdr. That makes this 2F over mdr t squared over 4 pi. So one of those cancels with that to leave me with a 2. Now let's plug in the values. Finally, I can get my n. So n is 40, 30 squared, 80, 2 times another 2 times pi. And I get 35.8 times. That was the number of rotations. What this problem is that you throw out, probably I would start from the position equation, and I would go, well, what do I know and what do I not know? Well, I didn't know alpha. But I do know alpha's relationship with torque and its moment of inertia. Solve for alpha. Well, what do I not know about this? and then just start plugging in moments of inertia and getting to a point where I could solve for a number. I need to know my alpha, so let's just plug it in there. 2 times 40 divided by 80. Oh, I love numbers when they cancel. Divided by 2, so it is 0.5 radians per second per second. That's its angular acceleration. Throughout the motion, it was accelerating at half a radian per second per second. Its final omega, alpha t, 0.5 times 30, or 15 radians per second. And so that gives you the final angular velocity of this thing. So there could be all sorts of questions regarding this. You have a rocket on a disk. It speeds up. Given these conditions, solve for this variable. You should be able to take these equations and go, now I know everything but tau. Solve for tau. I know everything but alpha. Solve for alpha. If you're able to solve for all of those variables, I can throw anything at you. A problem that could show up. We have there's an itty bitty bug slapped onto a disc. The disc's radius is 5 meters. That bug is opposite of a rocket engine. Yes?
On that question, why did they solve for n instead of using 40 meters? What does that n stand for?
N stands for the number of rotations. Yeah. Sometimes just saying it out loud, it really, well, a part of your brain just screamed out and goes, how'd you listen to me? So we have a bug on a disk. That disk is going to rotate from scratch, from nothing. I want to know what's the force of the rocket engine at 60 seconds. The bug's radial acceleration is equal to 40 meters per second per second. That the bug has a radial acceleration of 4 Gs, effectively. So I want to know what F is. I want to know what alpha is. I want to know what the final omega is. I want to know how many times did this thing rotate in the 60 seconds. And then we'll go from there and try another example. So if I say A sub r is equal to 40, you know for a fact that AR is equal to V squared over R. That we're able to get a relationship with that. If I know my radial acceleration, which is V squared over R, and that at 60 seconds, it's 40 meters per second, I know that omega is alpha t. Omega is omega naught plus alpha t, but I said it started from rest. I also know that V is equal to omega r. This makes this omega squared r squared over r. So radial acceleration can be rewritten as omega squared r. One of the things that, we'll take a brief pause so that I can explain something. There's typically a multiple choice question. And it says, you are on a disk that's rotating, and you walk further away from the center of the disk, does your radial acceleration increase or decrease? So, the big error that people make is they make the observation that, yes, AR is V squared over R. So if R increases, that means that radial acceleration decreases, which is incorrect. The problem that they have is that they didn't recognize the fact that that V is R dependent. So when you substitute V with omega R, you end up with omega squared R. And if you end up with omega squared R, then if R increases, then radial acceleration increases. And so that is a typical pothole that a lot of students just fall into during tests. So we know radial acceleration, that was given. We know that V is omega R, so AR is omega squared R, and that omega is equal to alpha t. So radial acceleration is equal to alpha squared t squared r. In this particular case, I know what t is, 60. I know what r is, 5. I know what AR is, 40. I'm just going to solve for alpha right now. So AR over t squared r. These types of problems are very substitution dependent. One of the reasons why I do that whole crazy M2 equals 9M1 deal is to get you used to the idea of substitution during problems. Is equal to alpha squared. So alpha is the square root of, hold on, let me rewrite it on another page. So alpha is 1 over time square root of AR over R. And this gives you 1 over 60, 40, 5, and my answer is 4.714 times 10 to the negative 2 radians per second. I'm writing it out to a few more digits so that I don't get bit rot, or as much bit rot as could happen. So we started with this, I ended up with this, I replaced omega with a term of alpha, and then solve for alpha, and then I end up with this. I get a number. Now this number is handy because 2 pi n, or theta, is equal to 1/2 alpha t squared. I could solve for n. N is alpha t squared over 4 pi, which means this is 4.714 times 10 to the negative 2 times 60 squared over 4 pi. Ooh, and I got the whole number in my calculator, so let's divide that. And I get 13.5 rotations. That it rotated 13.5. The other thing about these types of problems are, and it frustrates a lot of the students, is that you can go in many different directions. I'm sure we could do this problem solving for number of rotations first or something else first. What's the force Well, actually, now we can get omega. Omega is omega naught plus alpha t. Alpha is 4.714 times 10 to the negative 2. Time is 60. So my final omega is 2.83 radians per second. And that's my final omega. The last thing is to find the force. Well, force is equal to, actually, sum of the torques, which is equal to Fr, is equal to I alpha. I know what my alpha is. We found that. So F is equal to I, or 1/2 mass of the disk, R squared, alpha over, oh, actually I should have used lowercase r squared. Exactly, I know, Friday. One of the r's cancels, and I'm left with mdr alpha over 2. And that will give me the force. That means I need to give you a mass for the disk. 80. So this becomes 85, 4.714 times 10 to the negative 2 over 2. .43 newtons. And so that is the force of the rocket. So if that 9.43 Newton force rocket pushes for 60 seconds, the bug will be experiencing a radial acceleration of 40 meters per second per second. So this is a typical thing that that we do. Now, in this problem set that was handed out right now, I'm just going to let you know. In problem set 1, or I'm sorry, problem set 6, problem 1. Problem 1 is the Fisher-Fury problem. So actually what I did is I pulled it out of a test and gave it to you. Problem 2 comes from another test, and one of the things that I want you guys to look at is when I do these problems, I got to make sure the numbers work, and I got to make sure that the numbers work well. And this down here, that time, yes, it is 100 times the square root of pi. That's a very odd time. It's like Dr. Eschenberg was trying to get the numbers to work right. So if you see something like that, you know that that square root of pi is going to cancel out with something and disappear. So it's kind of hinting that I'm tipping my hand and letting you know that this is there. In this particular problem, I'll do something similar to it, and then you can just copy the procedure and go with it. I have, now these numbers, I have no idea if they're going to work or not. The mass of the disk is 100 kilograms. There is a force of, oh wait, thank you. There is a force of 200 newtons. So from rest, it rotates 100 times in 120 seconds. Now the mass of the disk is 100. It has a radius of 4 meters. Welded onto the disk directly across is a bar. The mass of the bar is unknown. So we've got like a merry-go-round. There's this big bar welded onto the disk. The rocket engine fires up. This thing spins 100 times from rest in 120 seconds. What's the mass of the bar? Now, hopefully the numbers work. So what do I need to do? Well, we've got a rotational motion situation. So I got 2 pi n is equal to 1/2 alpha t squared, because theta is equal to 1/2 alpha t squared. I know that the sum of the torques, which is equal to F times R, is equal to I times alpha. Now, I don't really need to know what alpha is. I don't ask for it. All I ask for is the bar. So what I'm going to do is I'm going to solve for alpha. Take that and plug it in there. So 2 pi n, I know what the value of n is, equals 1/2 FR over I t squared. I know what R is, I know what F is, I know what T is. The only unknown in this problem is I. And so what I could do to make this thing a little bit easier is actually find what the value of I is, the moment of inertia of the system. So I is equal to FRT squared over 4 pi n. I comes up, 2 pi n comes down, meets the other 2 and becomes a 4, and then you got FRT squared in the numerator. This becomes 200 times 4 times 120 seconds divided by 4 pi times 100. That 4 cancels out with that 4. Should have made the time 100 seconds. And I get 9167.3 kilograms meters squared. So if I simply asked for what the moment of inertia was of the system, you would get that number. Well, now that I have the total moment of inertia, what is that total moment of inertia? It's merely the sum of the 2 moment of inertia of the system. So the total is the moment of inertia of a disk plus the moment of inertia of the bar welded onto it directly across. Now in this particular case, the bar, the center of mass of the bar is at the rotation point, so we don't have to deal with parallel axis theorem. The disk, 1/2 mass of the disk R squared plus 1/12 ml squared. L is the length of the bar. So if L is the length of the bar, what is it in terms of radius of the disk? 2r. So this becomes 1/2 md r squared plus 1/12 m, actually this is the bar, 2r squared. This becomes 1/2 mdr squared plus 4/12 mb r squared. This becomes r squared. Oh, actually, I'm not going to factor that out at all. So I get this. The whole goal is to find the mass of the bar. So I move this over there. I minus 1/2 mass of the disk r squared is equal to 1/3 mass of the bar r squared. So 3 over r squared. I minus 1/2 md r squared is equal to the mass of the bar. So the rest is just algebra. But using our knowledge that the moments of inertia add up, much like just standard mass, we're able to algebraically manipulate it. There are times where I take this I, and I know that this I is this, and then solve for MB with all that around it. But that gets a bit cumbersome at times, especially for you guys. So that's why I solved for I and then went through it. So this is 4 squared, 9167.3 minus 1/2 mass of the disk 100 r4 squared, and that gives me the mass of the bar. Minus 50 times 16 times 3 divided by 16. So 1568.9 kilograms. And so we get this. Now, if you follow that procedure, you'll be able to solve problem 2. And in the lecture from yesterday, you should be able to do the, because all that dealt with alpha equals 0, you should be able to do the Fisher-Fury. It's a fairly straightforward. And so that is typically what we're going to do. So what I'm going to do now, I think we've covered everything that we need to do, so I'm just going to go over some problems that I know have creeped up. This one is a torque bar problem. I put it on the test and the students lost their ever-loving minds. It was a problem that I was working on for like a year, well, off and on, definitely for a year. And I told my dad about it, and he was like, please don't do that. It'll only confuse them. But it's easy. You've all seen Harrier jets. The jets that just sit there in the sky and don't do anything. And let's say, for instance, that the center of mass of the Harrier jet, the mass of the jet is, I don't know what masses of jets are, but let's say it's 10,000 kilograms. And so that jet typically has 2 engines on it that are pushing thrust upwards. And one is here, and the other one is there. And I give you that the distances from there to there is 6 meters, and the distance from there to there is 2 meters. And we'll call that R1 and R2. So given this information, the mass of the jet, the fact that you're on Earth, what are the 2 forces holding that jet up? What's the thrust of those engines on the front and the back? And that's what I threw at them on a test, and they just went nuts. Because it's not resting on anything. There's no fulcrum. How can there be a torque bar if there's no fulcrum? Well, a fulcrum is kind of like a state of mind. one of the things that you know for a fact is it is not moving up or down. It is not moving left, right, forward, back, and it is not rotating. And not only is it not rotating, it's not rotating about that point, or that point. So what we do is we do the same procedure. Sum the torques around a point. I'll call that point A. The two sensible points are this point or that point. Why? Because the distance from that force to that rotation point is 0, and so I've eliminated one of the two unknowns. In this particular case, I've eliminated F1. So the sum of the torques around A is 0. That means I have two torques, R1 MJG, and then R1 plus R2 F2. And so I have my two torques there. Now, this is the rotation point. Yes. Oh, stretching. Okay. In both cases, the mass of the jet and F2 are to the right of our point A. So for MJ, it's to the right and down, thumb into the board, or positive or negative. F2 is to the right and up, thumb points out and is positive. So it's negative, positive for the signs. $25,000 newtons. Now that I have that, F2 comes into play fairly quickly. Sum the forces vertically. F1 plus F2 minus MJG. So MJG minus F1 is equal to F2. So that is 10,000 times 10 minus 25,000, and that means that F2, or I'm sorry, whoa, I got everything bunched up. Oh, that's a 2, that's a 1, so F1 is 75,000 newtons. And so that's the Harrier jet problem. And it illustrates a point that frustrates students. You don't need an actual fulcrum to have rotation. It's not rotating about the nose of the plane, the back of the plane, the center of mass of the plane, the canopy of the plane, all that stuff. And because it's not rotating, you can do that, and you know it's not rising or falling, so you can do that. And so in all of these torque bar procedures, it's the same thing over and over and over again. We'll do one problem and then that'll be it. Open it to the floor. Do you have a homework problem that you want to talk about? Or do we all know all of physics? Yes.
start out just writing out an R1 and J and then G, why on the second one do we do R1 plus R2 F2? Like, why don't we just do
Okay,
this?
let's talk about this. So here's our diagram, and I'll blow it up. So A is the rotation point. Question, what is the definition? Give me an equation for torque. Bueller. It's R with F. F is the force. Well, what's R? R is the distance from the force to the rotation point. Here I chose A as the rotation point, the point directly beneath F1. There are two torques, one from the mass of the jet, the other one from F2. What's the distance from the center of mass to the rotation point? R1. What's the distance from F2 to F1? R1 plus R2. So depending upon where that point is with relationship to the force, those distances could change. Yes?
So if the rotation is around the center of mass, then R1 still be 2.
The distances won't change. It's just that if I started, let's say I chose that as my rotation point, then the two torques involved would be F1 R1, the distance from point to force, R1 times F1, and then F2 R2, that force times that distance. And so it's, in this particular case, it's not very useful because the two forces are unknown initially. So it's not a useful equation, but it illustrates the point. Let's do So we have, oh, I did this whole problem and no one saw it. So we've got a little bit of a change. We've got a torque bar problem. This will be the last problem, then we'll call it a week. It's a torque bar problem. We've got a fulcrum clearly marked by the triangle. We've got a 10 kilogram mass on the right of for M1. R1 is 2. R2 is also, well, oh, that's not to scale. Let me make it 1. R2 is 1. R3 is 1.5. The tension in the cable is 500 newtons. So the two questions are, what is M2 and what is that force there? So it's like a teeter-totter with a rope pulling up on that side. I got a 10 kilogram mass over here. I got an M2 over there. Unknown. What is my F? You do the same procedure. Sum your torques. You sum your torques around a convenient position. Probably what I would do is I always would just attack it at the fulcrum. A, I've got 1, 2, 3 torques. M2G is one of the forces, tension is the other, and M1G is the last one. Torque is the force times that distance from the rotation point that you've determined to whatever force you're studying. So the distance from there to there is R1. The distance from there to there is R2. But the distance from there to there is not R3, it's R2 plus R3. Now we do the signs according to the right-hand rule. M2 is to the left of the fulcrum and down, so it's a positive. Tension to the left of the fulcrum is up, or negative. M1 is to the right and down, or negative. So it's positive, negative, negative is the signs. And that's all equal to 0. The only unknown in this particular equation is t. That effectively goes over there and becomes this. That stays there, minus M1G. And so I get this. So 1 over 1. Oh, idiot. I'm referring to myself. What am I doing wrong? I gave you T. I'm looking for M2. But that's the benefit of alphabet soup mode. I could just go, all right, where do I go back? I need M2 right there. So TR2 plus M1GR1 is equal to M2GR2 plus R3. So TR2 plus M1GR1 divided by GR2 plus R3 is equal to M2. So that makes it 500, 1, 10, 10, 2, 10, 1 plus 1.5. Did I get all the signs right? I think I did. 500 plus 200 minus, or not minus. Minus, okay, whatever. Divided by 25. And I get 28 kilograms. Yeah, okay. So it's 28 kilograms. And now I can find F because sum of the forces in the vertical is equal to 0. F plus T minus M1G minus M2G. I need to know what F is, so M1G plus M2G minus T is equal to F. 10, 10, 28, 10 minus 500 is equal to and it's gonna be a whoopsie. How is that? Okay. So really, the procedure is, did I make a mistake in calculating 28? Hold on, start from here. So this one and that one go over. That one becomes positive, that one becomes positive. So TR2 M1 GR1 divided by GR2 plus R3, tension is 500. 10, 10, 2 divided by R2 and R3, 1 and 1.5. Because I'm ending up with a negative number. Because the answer that I'm going to get, and if sometimes during the calculations, this is now I've got a mystery, I got to figure this out. I got an answer of, oh, well then I guess it's just numeric. This is physically impossible. Minus 120 newtons would be the answer for it. This is one of the problems that you get by dynamically creating physics problems on the fly. Physically, it's not possible. What would happen is the beam would fly off or do something, and it's just not. It's not going to behave properly. When I do the problems on the test, I make the numbers work out right so that they're sensible. The fact that they didn't work out here is no big deal. The procedure is still ironclad. You just follow the procedure. There was one time I ended up with a problem like this, and so what I did is I announced to the class, the numbers are going to be crazy, expect an F less than 0, and then gave them a hint and just let them deal with that. But the procedure, there's nothing wrong with the procedure. So that's it. Have a good weekend. I will. See you later.